Hi, I'm Juna, and I'm a PhD student at Postec. I will present our paper, Deep Hough Voting for Robust Global Registration. Point cloud registration is the task of estimating the rigid transformation parameters that best align partially overlapping point cloud fragments. The objective of the task can be formulated as the shown equation, where it can be seen that it's a dual problem of finding inlier correspondences and optimizing transformation parameters that minimize the geometric error. Therefore, a good registration pipeline should use discriminative feature descriptors to estimate precise pointwise correspondences, and robust optimization algorithms to estimate accurate pose from the estimated correspondences. Point cloud registration pipelines are commonly implemented in a modular design. First, the local features from the input point cloud pair are extracted. One could use classical feature extraction methods such as FPFH, or learning-based methods such as FCGF. The extracted features are matched by nearest neighbor search in feature space, resulting in a set of putative correspondences. Next, outlier rejection methods can be applied to filter out outlier correspondences. Heuristic methods for outlier rejection include mutual nearest neighbor test and tuple test. Recently, learnable outlier rejection methods have been proposed to filter outliers in high-dimensional space. Finally, the pose estimation algorithm predicts the rigid transformation parameters. Ransack is still a very widely used classical method, but recent learnable methods such as PointNet-LK or DGR has shown better results. Among these modules, our paper proposes a new pose estimation algorithm. We address the limitations in existing registration methods, including weak performances on low overlap and high outlier ratio, difficulty of generalization to unseen data, and lack of scalability to larger scale datasets. To address these limitations, we propose a key idea, which is to view the registration problem as consensus maximization problem using Hough voting. From noisy candidate correspondences, we accumulate votes, or consensus, into discrete bins of the 6D parameter space. To this end, we proposed DHVR, Deep Hough Voting for Robust Global Registration. Here is the overview of our method. Our method is comprised of 3 steps. We first extract local features from a point cloud pair using fully convolutional geometric features, then compute the putative correspondences between the point clouds using the nearest neighbor search. Then, we sample triplet correspondences from the set of putative pointwise correspondences, since using all possible combinations of selecting triplets is intractable. Here we use a simple tuple test as a geometric constraint. Considering triplet correspondences, the tuple test checks the following point-to-point distance conditions. In other words, it tests whether all ratio of edge lengths of triangles in each point cloud is within a predefined threshold value. If all 3 ratios satisfy the constraint, the triplet is selected as valid sample. We repeat this for predefined number of random trials. After we build the set of triplet correspondences, we perform a voting. To cast a vote, we first need to retrieve the optimal rotation and translation parameters that minimize the geometric errors for each triplet. We use Procrusta's method, a closed-form solution for this equation. For compact rotation parameterization, we adopt axis angle representation. Finally, we quantize the rotation and translation parameters to identify the bin index. All voting procedures are parallelized and utilize sparse tensor for efficiency. After all the votes have been cast, we apply 6D sparse convolutional network to refine the Hough space adaptively. To train the refinement network, we supervise it to perform a binary classification task where the true class is the bin which ground truth transformation matrix falls into. We trained our method on real-world indoor dataset, 3D match, and compared registration performance with various baseline methods. We measured translational error, rotational error, and recall as evaluation metrics. Our method yields the best accuracy in all metrics while showing the high efficiency. Furthermore, to validate the R method's robustness to the lower overlap pair, we evaluated on 3D low match dataset, the recently constructed low overlap dataset from 3D match. We outperform the recent learning-based outlier rejection method by large margin. Finally, we evaluate our method on outdoor dataset, Kitty, and the multi-way registration dataset, ICCV2021, to validate the generalization ability of our method. Our method have shown competitive results with the previous state-of-the-art method on both. Note that we used the network trained on 3D match for multi-way registration experiment without any fine-tuning steps, which shows the good generalization ability of our method. Thank you for watching. Please check our paper or visit our poster session for details.